1.3 rates of change. So we're going to recall dependent variable, usually denoted as y. This can represent quantities such as volume, air temperature, and area. Okay, so the dependent variable depends on the independent variable. This is the one that we usually control, okay, represented as x. And then these can represent quantities such as height, elevation, length. Okay, we often have interest in how rapidly the dependent variable changes with respect to the change in the independent variable. The independent variable is usually like more the controlled one. Okay, in 1.3, so like this rates of change, we will show that an instantaneous rate of change can be calculated by finding the limit of the difference quotient in some way that we can find the slope of the tangent. Okay, so this is a continuation of yesterday. Okay, let's talk about velocity as a rate of change. This is one of the most commonly used applications. So an object moving in a straight line is an example of a rate of change model. Okay, so object moving in a straight line, it's going this way. Okay, when the line moves upwards, it is considered to be a positive direction. And when the line moves downwards, it's considered to be in the negative direction. Okay, this positive direction and negative direction have not come into place in mathematics in high school yet. We will cover this more in vectors. Okay, so example, a car moving on a highway traveling 340 kilometers in 4 hours. Okay, so the average velocity would be, if we would take that 340, we would divide it by 4, right? So distance over time, and then that's going to be your velocity. So the average velocity is change in position over change in time. And then we're going to get a rate. Our rate for this one would be, for example, 85 kilometers per hour. Okay, so we use S at t to represent the position of the vehicle in a straight section of the highway at time t. Okay, so whenever you see this, this is usually displacement. Okay, and from the displacement, we can find velocity. Okay, so that the average velocity is the difference in displacement over the difference in time. Okay, average velocity. If the position of an object at time t is given by the function s at t, then in the time interval from t equals a to t equals a plus h, the change in position, so delta s, and remember a and then a plus h is just those x values, right? Whatever x value that is, and then whatever h is. And as a recall, in grade 12, we used h equals 0.1, h equals 0.01, h equals 0.001, and we got closer and closer along this curve until we had the smallest difference in h, right? So h approaches 0. So the change in position is delta, I don't like this delta s over here. I would rewrite this here. Delta s equals s at a plus h minus s at a. That would be that numerator, right? Change in position. And then therefore the average velocity is that change in position over h, right? Because the change in time is actually approaching 0. Because this h value is going to go smaller and smaller and smaller and smaller. Okay, example 1. Without knowing how fast your car is traveling, your odometer readings are as follows. So maybe like while you were traveling, you took a look and you're like, okay, it's been 1 hour. I went 62 kilometers. It's been, or sorry, 0 hours. Like that would be the start. I went 1 hour, I'm at 133. I'm at 2 hours, 210, 2.5, 3. So you can see that this independent variable here is not going up by the same amount. It's going up by 1, 1, a half. And that's okay. Okay, so this is the time in hours, so t at h. And this is the displacement, s at t. Okay, so determine the average velocity of the car over each interval. Okay, so this is a little laborious, but each interval. So we're going to go interval 0 to 1. Okay, so the average rate of change from 0 to 1 is going to be 133 minus 62 over 1 minus 0. And we're going to get 71 kilometers per hour. Okay, and we're going to do the same thing for interval from 1 to 2, interval from 2 to 2.5, and the interval from 2.5 to 3. Okay, so the AROC, average rate of change from 1 to 2, so that's these 2 points here. We would do 210 minus 133, and then 2 minus 1 in the denominator. Okay, and I get 77 kilometers per hour. Now the interval from 2 to 2.5, so these ones here. So again, the average rate of change is 250 minus 210 over 2.5 minus 2. So for this one, there's a little bit more math because the denominator is not just 1. So I'm going to say this is going to be 40 over 0.5, which is 80 kilometers an hour. Okay, and the average rate of change for this last one, we're going to go 293 minus 250 over 3 minus 2.5. So I get 43 over 0.5, which is 86 kilometers per hour. Okay, so we did A. B. If the speed limit is 75 kilometers an hour, at any point during your drive, were you speeding? So, yes. Between hours 1 to 3, right? So the interval, like 1 to 2, speeding. Not by much, but still speeding. Interval 2 to 2.5, speeding, right? All of these numbers here are over 75. And interval 2.5 to 3, speeding. So in total, it would be from 1 all the way to 3. Okay, and C, explain why there may be other times when you are traveling above the posted speed limit. Okay, so why in real life would you travel above the posted speed limit? Okay, possibly late for work, possible medical emergency, maybe you had to go to the bathroom. Maybe you were just passing someone. You could just be going the flow of traffic. Maybe that traffic is just all going, say, 80 kilometers an hour, so you're just going with the flow of traffic. So late for work / in a rush. Yeah. So those are all valid reasons. Now, D, compute your average velocity over the interval 4 to 7 if S at 4 equals 375 and S at 7 equals 609. Okay, So D, we're going to go average rate of change equals 609 minus 375 over 7 minus 4. So we're going to get 234 over 3, which is 78 kilometers per hour. Okay, and if you want, you can write, therefore, average rate of change from 4 hours to 7 hours is 78 kilometers per hour. Okay, example 2. A pebble is dropped from a cliff 80 meters high. After t seconds, the pebble is s meters above the ground, where s at t equals 80 minus 5t squared. And this is on the domain 0 to 4. Okay, so there's some cliff, pebble is dropped. Okay, 5t squared is giving us a parabola. So there's going to be some vertex, and it's going to be from 0 to 4. This is going to be in time, and then this is going to be in height. Okay, so A, calculate the average velocity of the pebble between times t equals 1 and t equals 3 seconds. So for A, we're going to do the average rate of change. Okay, if we want to actually write out the formula, this is going to be f at 3 minus f at 1 all over 3 minus 1. So what we can do is we can go ahead and sub in. We can do the work on the side of the board if we want. So let's go s at 3. Actually, let's change these to s's. We're going to change this and this to s's for proper form. Okay, s at 3 minus s at 1. So s at 3 is going to be 80 minus 3 squared, which gives us 35. And then s at 1 is going to be 80 minus 1 squared, which is going to give us 75. So we're going to go s at 3, which is 35, minus f at 1, which is 75, over 3 minus 1, which is 2. So I get negative 40 over 2, and I get negative 20 meters per second. Okay, so average velocity, let's just put average velocity is 20 meters per second. Okay, and that 20 meters per second is negative. Okay, now calculate the average velocity of the pebble between the times t equals 1 and t equals 1.5 seconds. So let's go ahead and find s at 1.5. So it's 80 minus 1.5 squared. Okay, and we get 68.75. Okay. Now let's find the average rate of change between s at 1.5 and s at 1. Okay, 1.5 minus 1 in the denominator, and we get 68.75 minus 75 over 0.5. So for the numerator, we get negative 6.25, and this is going to be over 0.5. When we divide those out, we get negative 1.25. Okay, so the average velocity here is negative 1.25 meters per second. So a big difference here, okay, and we got to think explain why your answers for A and B are so different, okay? So let's take a look at where S at 1 is. So possibly at 1, we're kind of talking about a vertex. And if we go between 1 and 3, And I'm not sure of this because I didn't actually do the math. I could, but I'm just going to talk approximately, okay? So between 1 and 3, we have a big difference going downward, okay? That's much more steep than between maybe 1 and 1.5. Let's call this 1, let's call this 1.5, okay? So a lot more steep. Also, when we're talking about a parabola, up here is going to be around the vertex. So it is, what that means is like when, say, a ball is thrown, a rocket is launched, here a pebble is dropped, okay? Around here, this is the turnaround point. So for just a second, it was maybe traveling upward, okay? And this one wasn't. This one was just traveling down. But now that I'm looking at the equation, but what ends up happening is this is like there's a turnaround point. So everything up near the vertex is going to be a little bit slower. And then gravity is going to pull that pebble down, and it's going to start to drop faster and faster and faster. Okay, so let's make a couple points. So this is quadratic. The slope is not constant. Okay, and the slope is constantly changing. Okay, so let's go. Continuation, constantly changing. Sorry, this is negative 12.5. Okay, instantaneous velocity. The velocity of an object with position function as at t at time t equals a is v at a equals the limit as the change in t approaches 0 of the change in the displacement over the change in time equals the limit as h approaches 0 of s at a plus h minus s at a all over h. Okay, so we've seen this before. Now the only thing different is that we're replacing the f at a with an s at a, right? Specifically displacement. So please note, here's the difference between speed and velocity. Speed. The speed of an object is the absolute value of its velocity, indicating how fast an object is moving. It only cares about how fast. It's always positive. Okay, positive numbers. Now, velocity, which is what we just did in the last example, and this is why I kept them as negatives, this indicates both speed and direction. Okay, so this is concerned with two things, speed and direction. We're going to get more into this when we do vectors. Okay, relative to a given coordinate system, this can be positive numbers or it can be negative numbers. It can be both. Okay, so example 3. A toy rocket is launched straight up so that its height, s, in meters at time t in seconds, is given by this equation here. What is the velocity of the rocket at t equals 4? Okay, so we can only see one point here, t equals 4. So that means that we are going to be using instantaneous rate of change. Okay, so let's do the 3 steps from lesson 1.2. We're going to do s at 4, and let's go ahead and sub it in. Negative 5 bracket 4 squared plus 30 times 4 plus 2. And we are going to get 42. Okay, and step 2, we're going to sub in s at 4 plus h. So negative 5, 4 plus h squared plus 30, 4 plus h plus 2. Okay, so negative 5. When we have a binomial and we square it, we want to expand this. So I'm going to first rewrite this as 4 plus h times 4 plus h. I'm going to expand this one as is. So 30 times 4 is 120. 30 times h is 30h. 1 plus 2. And now we have 3 terms multiplied by one another. So I'm going to bring down the negative 5, and I'm going to FOIL what's in the brackets. So 4 times 4 is 16. We're going to get 4h and 4h, which is 8h. And then we're going to get h squared here. H times h is h squared. Okay, bring down the 120, bring down the 30h, and bring down the 2. Okay, now we're going to distribute this negative 5 into the bracket. So negative 5 times 16 is negative 80. Negative 5 times h is negative 40h. And negative 5 times h squared is negative 5h squared. Okay, and bring down the rest. And at this point, we can go ahead and collect like terms. So negative 5h squared is going to go first. Negative 40h plus 30h, I get negative 10h. And then we have negative 80 plus 120 plus 2, I get 42. Okay, now step 3, we are going to sub this in to the limit as h approaches 0 of s at a plus h minus s at a all over h. Okay, so the limit as h approaches 0, so we're going to sub in s at a plus h, which is negative 5h squared minus 10h plus 42, and then minus s at a, which is 42, so minus 42, and this is all over h. Okay, 42 and negative 42 cancel out. So in the next line, what we can do is we can factor out the h. I'm not even going to factor out the negative here. I'm just going to factor out the h because then it's a clean cancellation in the numerator and denominator. So I'm going to write negative 5h and minus 10 in the bracket. Okay, we know that these two h's cancel out. So we are left with the limit as h approaches 0 of negative 5h minus 10. Okay, at this point, we sub in h equals 0. We drop the limit, and we have like negative 5 times 0 minus 10, and we get negative 10. So therefore, this is going to be negative 10 meters per second. But because this is talking about velocity, we have to think, can this be negative or does it have to be positive? Yes, with velocity, we can have a negative number because it's talking about speed and direction. Okay, so let's just write therefore the velocity of the rocket at t equals 4 is negative 10 meters per second. So let's highlight the difference between the average rate of change and the instantaneous rate of change. Okay, so the difference quotient, delta y over delta x equals f at a plus h minus f at a all over h, is called the average rate of change in y with respect to x over the interval from x equals a to x equals a plus h. Okay, just don't forget in the denominator that would have been a plus h minus a, right? Off with h. Now, the instantaneous rate of change, we can say, therefore, we conclude that the instantaneous rate of change in y equals f at x with respect to x is x equals a, or when x equals a, is the limit of delta x equals 0. Okay, the change in x as it gets closer and closer together as it approaches 0. Okay, of delta y over delta x equals the limit as h approaches 0 of the same numerator here, f at a plus h minus f at a all over h. Here's the difference, okay? This is basically telling us we have 1 point that we're working with. This here with no limit is telling us we have 2 points. We have 2 points that we're working with. So as soon as you see limit, it's instantaneous rate of change. Okay, so example 4. The total cost in dollars of manufacturing X calculators can be given by this equation here. C at X equals 10 root X plus 1,000. Okay, so A just asks, what is the total cost? Right? And when it says total cost and then it gives a C, the C, it implies that the C is representing cost. Okay, so I'll put like representing cost. So what is the total cost of manufacturing 100 calculators? Well, that's just a straight sub in. What is the cost at 100? Okay, so let's sub in 10 root 100 plus 1,000. Okay, 10 times root 100 is just 10. And then plus 1,000. So that's 100 plus 1,000. So 1,100. Okay, so total cost of 100 calculators is $1,100. Now B asks, what is the rate of change in the total cost with respect to the number of calculators X being produced when X equals 100? So again, we're only given 1 point. So we're going to do the 3 steps. A can represent like the first step. Now, step 2 is going to be the cost of 100 plus H. So we have 10 root 100 plus H plus 1,000. Okay, and we can't do anything to that. Just remember, whatever's under the root sign, it acts as though it's in a bracket. So we can't root 100 plus H. So we can't just root the parts of this. We have to root the entire thing, and we can't. So we'll just leave it for now. So step 3 is going to be the limit as h approaches 0 of f at a plus h minus f at a all over h. So let's go ahead and sub in. So equals the limit as h approaches 0 of 10 root 100 plus h plus 1,000. Okay, minus 1,100. We can do all over h. Okay, I don't like to write the h like this. So what we're going to do in the next step is 2 things. We are going to multiply by the conjugate. So 10 root 100 plus h plus 1,000. Actually, I'm gonna simplify this right here. Plus 1,000 minus 1,100. I'm gonna go to minus 100. Okay, now I'm going to multiply by the conjugate of this. So this we can kind of bracket, keep it together so that we can just follow with our eyes. Okay, so 10 times 100 plus h plus 100, and then that's going to be over 10 times 100 plus h plus 100, right? Because this is just like multiplying by 1. It's not changing our equation, is just making it look a little bit different. And then we're going to divide by h. Okay, leave that over there. So let's go ahead and expand. So 10 times 10, our coefficient here is actually going to be 100. Then this root times this root I'm going to keep it in brackets, and it's going to be 100 plus h. And I'm keeping it in brackets because we're going to have to expand this. Okay? The middle two terms cancel out. You don't have to write them anymore. So this 100 times 10 in the root minus 100 times 10 in the root, they're going to cancel out. That is the whole point of doing the conjugate, right? It's the difference of squares. And then the last term is going to be minus 100 times 100. There's going to be 4 zeros there. Okay? Keep this denominator as it is. It doesn't matter. It's going to work out anyways. And then that's times 1 over h. So let's go ahead and distribute in. We're going to go limit as h approaches 0. 100 times 100 is 1 with 4 zeros. Plus 100h minus 100, or sorry, 10,000. All over the same denominator. Okay, and then times 1 over h. Okay, so 10,000 minus 10,000 goes away, and we get the limit as h approaches 0. Oh, I don't know why I did an underline there. Okay, we get 100h in the numerator, and that's over 10. 100 plus h plus 100 times 1 over h. At this point, we can cancel out the h's, and we are left with the limit as h approaches 0 of 100 over 10, 100 plus h plus 100. Okay, let's sub in h equals 0. So in the denominator here, we're going to sub in 0, which is just going to go away. So we're going to have 100 over 10 times, well, what's the root of 100? 10. I'll put this in so you guys can see it. Okay. We're going to get 100 over, that goes to 10. So that's 100 plus 100. So we're going to get 100 over 200, which is 1/2. So we can say, therefore, the rate of change in the total cost with respect to the number of calculators produced is 1 over 2. This is going to be dollars per calculator. So let's put 50 cents per calculator. And then we have the rate on there, right? The dollar and then the calculator.